One of our lab work related to federated learning. So I'm representing one of the teams of my lab, and which works on the federated learning architecture for edge computing environments. So I know you are all intelligent and it's an industry day, so just bear with me. So before we go, we want to see like what are these technologies and what are the advantages and what are the challenges when we combine those technologies. So as edge computing, it brings resources, computational resources, memory resources near to the user devices. So it reduces latency and saves the bandwidth, and it doesn't have to go to the centralized cloud all the time. So it saves the cost for the data travel. And when we talk about the federated learning, so as we know, so it's a collaborative training environment, and without exposing the data to the outside world. So when we combine these two technologies together, so we get both the advantages, but it also multiplies their challenges, which is like their vulnerabilities in federated learning in their own aspect, and edge computing has its own vulnerabilities in its own aspect. So when we combine those things, so it becomes a bigger challenges. So and also as 3GBP latest releases, last 3 releases, they are specifically targeting FL as a key enabler for 6G computing. So there's a potential to work on FL and edge computing combination. And also our architecture, the architecture that I'm presenting today is basically inspired by the fundamental theorem of distributed data systems, which is CAP, which says that ideally we want these 3 parameters to satisfy. But at any given scenario, we can only satisfy 2 parameters, and we have to trade off with the 3rd parameter. So taking inspiration from that, we also suggested a theorem that at any this heterogeneous federated learning and edge computing environment, we ideally want these 3 parameters: convergence, accuracy, and tolerance. Tolerance covers all the real-time, you can say, or malicious activities, and fault tolerance, resilience, everything here. So we say that at any given time, only 2 parameters can be satisfied given the situation. So based on this, we proposed our architecture. So for this talk, I will be only presenting with the statistical heterogeneity. I'm not covering the system heterogeneity and network, which we have already covered to justify the suitability of the architecture. So, so in this we first like see what is the heterogeneity and what is the heterogeneity within the heterogeneity. From the statistical perspective, there is labels, quantity skew, and then there comes a feature skew when we talk about the real data sets, and then there is a temporal skew as well. With that, there is also model architecture heterogeneity. So it's a bit complicated. So to target this thing, so we devise, like this is an edge computing environment. So we are devising 2 levels of aggregation. So one, because we already have this edge and it is near to the user, and the federated learning is a client-server architecture, so we can have this aggregation for one kind of, not for one layer of aggregation. And for the second layer, it is basically not on the client, but basically on all the models that all the edges are currently operating. So from the concepts of cloud computing, so we have this fog concept. So we are utilizing that fog to aggregate all those edge models and see how we can learn, and we can merge together to make a more better global model, and we can deal with different kind of clients. So in similar way, like data is not exposed, it's only the model going layer by layer, and there also identity is saved in each layer. So for this for the second layer of aggregation, so we are finding the similarity because as we take the edge models from different edges, so because it's a distributed environment, so when we take different edge models, so we have to find the similarity. So right now in this model we are using this KLT similarity, and for the clustering, because we cannot fix these number of clusters for the edge model, so we are taking we are using PCA to indicate a factor which is going to be used as a clustering method. So it's gonna be a dynamic, so it's not hard and fixed. So it improves the personalization and robustness in highly non-IID scenarios in respect to model architecture and in respect to data diversity. And also this, we made sure that it aligns with the 3GPP visions and their guidelines about their edge intelligence and data, edge analytics. And so we propose this architecture. So right now I'm using only one fetch to show you only one fog layer. But you can imagine that with one fog layer there are many edge nodes, and they are training in the distributed fashion. Sorry, I will be very quick. So this is the proposed architecture, and then here we are just using the benchmark data set. So we tested on 3 benchmark data sets, and 3 are telecom related data sets. And the purpose of doing the benchmark data set to prove the concept that this is how it is different. Like when we have to do the comparison, then you do the comparison with the benchmark data sets. Although I know that this is not a realistic data set, but just for the comparison. So in this we came to know that it is performing well, and also we didn't use multi-edges. We only used one edge to do the comparison because the traditional methods are client server, so we cannot use the same scenarios for different edges, otherwise it's not a good comparison. So we use this client specific results, and then we also had this generalizable, so in which we use 500 clients on each node, and then we see like is it able to generalize these models or not. So it performed very well, and there's a loss. So it's also, you can say that after the edge level it is going to be a transfer learning process between all the edges that one fetch is connected to. So yeah, so my takeaways is the hierarchical aggregation for the edge computing environment, and cluster-based multi-model sharing, and yes, it will create the robustness among the diversity of the model and data. Thank you very much.
Thank you very much, Satwat. Do we have any questions in the room?
Really interesting talk. Thank you. Can you please expand a bit more on the CAT theorem part? Is it like a theoretical trade-off that you can prove?
Yes, we did. I mean, you can check my paper, or I can talk to you, because yeah, we made the comparison, and then we theoretically proved that okay, this goes, for example, like consistency means like. So it's showing here as well. So everything should be identical. Data should be always available and in the same position. So we are making this analogy with the convergence, like the convergence of the global model. Because if the global model is always changing, so it is disturbing the clients or the personalized behavior. So we want it to be consistent for all different kinds. So all the time we want global model to be very intelligent or to be trained. So this is one of the kind of the relation, and availability is equal to the client level accuracy. So, for example, if you are looking towards having a good global model who is performing well, then you have to compromise on the personalized, because this will not be working on the heterogeneity. But if you want that my global model is good and all my clients are satisfied, so it means that you are talking about the homogeneous, you are compromising on the heterogeneity. So there is always one thing that is being compromised. And yeah, so.
Thank you.
Thank you again. Great talk.
Thank you so much.